One of the things I find fascinating about astronomy is how the great discoveries fall into the context of my personal life. And perhaps you find this also. So in 1998, I graduated from Christian Brothers University. And here you can see a picture of me and my brother right outside around the corner from where this presentation is, out front by the Tau Beta Pi Bent. And 6 months later, this issue of Science magazine was released. And this was featuring the discovery of the year in 1998, the breakthrough of all sciences, and that is the discovery of the accelerating universe. Now, as a result of this discovery, these three gentlemen won the Nobel Prize in 2011. Saul Perlmutter of the Lawrence Berkeley Laboratory, who was the leader of the Supernova Cosmology Project, Brian Schmidt, who was the leader of the competing high Z redshift supernova team, and then Adam Riess, who was the co-author on the Schmidt paper, and he actually did the measurements of the data that led to the discovery of the accelerating universe. And the model that they discovered is completely counterintuitive. Basically, if you did a pie chart of the mass energy content of the universe, this is basically how it would break down. 23% dark matter, not made up of the same stuff that you and I are made up of. Roughly 73% dark energy, and then this very small sliver right here represents everything else that you and I can see and experience. Basically, there are more stars in the universe than grains of sand on all of the beaches and deserts of the earth, and yet all of these stars added together, along with everything else that we can see, comets, moons, planets, people, etc., makes up less than 0.5% of the stuff of our universe. We now believe that the dominant stuff of our universe isn't even matter at all. It's energy, a mysterious dark energy that's causing the universe to expand more quickly with time and leading to a runaway universe. And that's basically what we're going to talk about tonight. So to set this up, we're going to talk about the discovery of the expanding universe, to start out with, leading off of Bill's presentation on cosmology, the 12th section of the short course in astronomy. We'll talk about the empirical evidence in the discovery of the accelerating universe, possibilities, dark energy possibilities, and then finally the fate of the universe. How does it play out? How does the story end? So to kind of set this up, 100 years ago, Albert Einstein published his general theory of relativity. It's a problem he worked on for 8 years, basically did nothing else. And here you can see the issue of Sky and Telescope magazine from December of 2015, celebrating the 100th anniversary of this discovery. And basically, general relativity is a shift, a paradigm shift in how we look at gravity. Gravity is not a force, it's an effect due to the curvature of space and time. Summing it up, matter tells space-time how to curve, and curved space-time tells matter how to move. The sun, or the Earth, orbits the sun, not because the sun pulls on the Earth, but because the sun's mass warps the fabric of space and time, creating a curved path that the Earth naturally follows as it orbits the sun. And that's why the Earth orbits the sun, and why the moon orbits the Earth. It's because of the distortion of space and time due to the presence of matter. But Einstein had a problem. All the galaxies in the universe have mass, and so they should all be pulling on each other due to gravity. So general relativity inherently predicted a universe that should collapse in on itself. It should either be expanding or collapsing, dynamic in some form. Now, 100 years ago, this was completely counterintuitive because the prevailing worldview at the time was that the universe is static and fixed and eternal. So to get around this problem, Albert Einstein did what any good theorist would do, and that is he introduced a fudge factor into his equations of general relativity, something called the Cosmological Constant, or Lambda, to act as a counter to gravity to balance out the universe. So to set this up, imagine this foamy stuff here is all the stars and galaxies, all the mass in the universe. And you have this blue arrow here, which represents gravity, which would cause the universe to collapse in on itself because everything is pulling on it. Everything that has matter calls out to everything else in the universe that has matter. The cosmological constant would be represented by this pink arrow, which is completely opposing gravity exactly equaling out gravity, which leads to a static universe. So that's the idea behind the cosmological constant. Well, it wasn't long after that George Lemaitre made a radical proposition, and that is he proposed that the universe had been born. It was not static and it was not eternal, but it actually had an origin. And here you can see a picture of Albert Einstein and a young George Lemaitre. Radical new idea, and it's something that Einstein didn't like. And here you can see an older Albert Einstein chastising a young George Lemaitre, basically saying, your calculations are correct, but your physics is atrocious. Well, unfortunately for Einstein, the data was mounting at this time, early 1900s, to support George Lemaitre's idea that the universe had in fact been born. And it really began with this gentleman right here, Vestal Slifer. He worked for the Lowell Observatory. He's actually the gentleman who hired Clyde Tombaugh, which led to the discovery of Pluto in 1930. But in the 19-teens, Vestal Slifer used his 24-inch telescope to systematically measure the velocities, the radial velocities of a handful of nearby spiral nebula, as they were called at that time. Again, for the previous 2 centuries, ever since people had been building telescopes, they looked through and they noticed these fuzzy patches, which they called nebula. Weren't sure exactly what they were, but the idea was that they were possibly gas clouds within our own Milky Way galaxy. Well, in 1917, he measured the radial velocities of the nearby spiral nebula and discovered that 21 of the 25 were redshifted, meaning that they were moving away from us. Again, if you filter the white light of star through a prism, you get the spectrum of colors. That's how we can tell what stars are made out of. You see hydrogen, ionized calcium, sodium, etc. The absorption lines of stars. Well, what Slifer discovered was the spectra of the nearby spiral nebulae were shifted toward the red portion of the spectrum. That meant that the light had longer wavelengths and that they were moving away from us. Similar to the audible Doppler shift, if you ever stand on a street corner and you hear the siren of a police car or an ambulance as it's approaching you, you notice that the sound is more high-pitched because the sound waves are being compressed as it's approaching you. But then as it passes you by, you hear more of a tired sounding. The sound shifts to the longer wavelengths of the sound because it's moving away from you. Same kind of thing in astronomy. If an object is moving toward you, then the wavelengths of light will be compressed toward the blue end of the electromagnetic spectrum. If it's moving away from you, the wavelength will be longer and it'll be stretched more toward the red end of the electromagnetic spectrum. So Slifer discovered this for the spiral nebula. We now know them to be galaxies. And the bottom line is the spiral nebulae were different from stars. So the same kind of thing was done with stars, but there was no systematic movement with regard to stars. Some had radial velocities toward you, away from you, sideways, whatever. There was a kind of a random motion to stars, but there seemed to be a systematic pattern to the spiral nebulae, and that is that they were all redshifted, meaning that they were all moving away. Didn't exactly know why. And it wasn't until this man came along, Edwin Hubble, in 1929, and discovered an empirical redshift distance relationship. And this is 4 years after the paradigm shift occurred. In 1925, Edwin Hubble published a paper resolving the mystery of the spiral nebula. Again, 2 competing worldviews for centuries. The nebular hypothesis, that the spiral nebulae were in fact gas clouds within the Milky Way. Early 1920s, the perception of the universe was it was the entire Milky Way galaxy, and then you had just little gas clouds that were part of the Milky Way galaxy, like the Andromeda Nebula. And then you had the competing island universes hypothesis, meaning that the spiral nebulae were actually systems of stars outside of the Milky Way galaxy, in fact, separate island universes. Immanuel Kant, 1755. Edwin Hubble measured the distance to the Andromeda spiral, figured out that it was in fact a separate island universe, and overnight expanded the size of the universe by a factor of 100 billion. It's just an amazing discovery. Well, 4 years later in 1929, picking up where Slifer left off, Edwin Hubble discovered that there was a systematic distance redshift relationship, meaning that the more distant the spiral galaxy was, the galaxies were, the faster they were moving away. And that led to the discovery of Hubble's Law, V equals H naught D. And you can see basically a linear relationship here. So the recessional velocity increases as the distance increases. Didn't exactly know why this was, but essentially what Edwin Hubble discovered was the systematic expansion of the universe. And it kind of, again, getting back to our raisin cake analogy. If you have a dough of raisin bread and you put it in the oven and it expands, the dough would in fact be analogous to the space in the universe, and each raisin would be analogous to a separate galaxy within our universe. So the reason why the universe is expanding is not because the galaxies are moving through some predetermined already existing space, but it's that space itself is stretching, or space-time is stretching, and just taking the galaxies along with it. So there is no center to the universe. We're not located in any special place, but it's perceived from our point of view as though we are in a special point in the universe because we see every other galaxy moving away from us. However, it's an illusion. If you were to contact an alien living on a planet orbiting a distant star in a distant galaxy billions of light years away, he would think he was at the center of the universe. It's just because that space is stretching in all directions within the universe. Another way to think of it, this is a classroom setting. We have individual chairs. Not necessarily the best setup in this room, but imagine a classroom where you had individual chairs and individual desks. And then I asked you to do a simple exercise. Every 30 seconds, get up and put 5 feet of space between you and your next door neighbor. And do it again. After every 30 seconds, you get up and put an additional 5 feet of space between you and your neighbor. What would we see? The size of the room would be expanding in all directions. Now, if you were sitting here, the person immediately next to you would only be moving a little bit. But the person on the other side of the room would be flying away from you because there's more space between you and the person at the other end of the room. Same kind of thing with the expanding universe. The more space there is between you and a galaxy further away, the greater the rate of expansion. That's the Hubble's Law. That's the systematic expansion of the universe. So after this was discovered, Albert Einstein revisited the cosmological constant idea, threw it out, and labeled it as his biggest blunder, and really missed out on an amazing opportunity to discover by first principles the expansion of the universe. And here you can see a very sad and despondent Albert Einstein. I don't know what he's thinking in this photo, but it could be something like this, Lambda, what was I thinking? But isn't it amazing and ironic that he discovered perhaps the most dominant stuff in the universe, essentially 3/4 of a century before the actual discovery was made. 1961, Alan Sandage, as cosmology develops as a legitimate science, basically said that cosmology is the search for 2 numbers, H naught, the Hubble constant, and Q naught, the so-called deceleration parameter. Now again, it was always assumed that even though the universe is expanding, it should be slowing down in its rate of expansion because all the galaxies are pulling on each other. That's why Q naught was set up initially as a negative number. It was always assumed that it would be decelerating in its rate of expansion, hence the term deceleration parameter. But if it's negative, if you get a positive number, then it actually leads to an accelerating universe. In 1990, the Hubble Space Telescope was launched and then fixed. Now, Hubble, not only a tribute to the man who made the initial discovery of the expanding universe, but also its real purpose, its mission. The main focus of the Hubble Space Telescope in the 1990s was to measure the Hubble constant, or the Hubble parameter. And this led to perhaps the most famous picture ever taken in all of astronomy, the so-called Hubble Deep Field. Every blob of light that you see here is a distant galaxy of at least 100 billion stars, like our Milky Way. There are 1 or 2 stars in this field that are background stars, foreground stars, if you will, in our own Milky Way galaxy. But basically, you have several thousand galaxies in here. Now, this image, the section of sky subtended by this photo, is the equivalent of a grain of sand held at arm's length, or about 1/25 millionth of the sky. You're looking back 12 billion years into the past. And for those of you taxpayers in the room, this image cost about $2 billion to take, and it was worth every penny of it. Take the Hubble Space Telescope, point it at the section of the sky where there's nothing going on, complete blackness, let it sit there for 2 weeks, collect photons, and this is what you get. Just an amazing image. Probably the most iconic image ever taken in the history of astronomy. Now, I took stellar and galactic astronomy in 1993, a couple years before the Hubble Deep Field was taken. And toward the end of the class, we got into cosmology briefly. At that time, it wasn't known what the ultimate fate of the universe was going to be. So you had different cosmological models. And you can see a snapshot here of my notes. And one of the ideas was you have an origin, Big Bang, an expanding universe that slows down with time, reaches a climax, halts, and then recollapses back to a singularity. And then maybe you have an oscillating universe where this process happens, collapses, and then it repeats again. So you have a Big Bang, expansion, then a big crunch. Big Bang, expansion, and then a big crunch, or an oscillating universe. The idea is Big Bang, expansion, halts, recollapses. Process takes about 80 billion years. Did you enjoy the show? Exact words of my astronomy professor. Another way to graph this out is the density of stuff in the universe is ultimately going to determine the destiny of the universe. Density equals destiny. So cosmologists, we want to know what the fate of the universe is. Is the universe going to expand forever, or is it going to expand for a while and then recollapse in on itself? So in a dense universe like this, if this is time equals now, you go back in time and you have a universe that has an origin and it expands. If you have a really dense universe represented by this parameter, omega matter, omega sub m is the density of the matter in the universe. You could have a universe that expands and then collapses. Or if you have a less dense universe, you could have a universe that expands, slows down in its rate of expansion, and then asymptotically approaches some value. So it just continues to expand for a while, slows down, and then just kind of floats. Or you can have a universe that equals where the omega matter equals the critical density. So based on measurements, cosmologists now believe that the matter density of the universe is about 30% of the critical density. The critical density being the total content to get a flat universe, spatially flat universe. So prior to the 1990s, it was assumed that matter was all the stuff in the universe. Basically, you had ordinary matter and you had baryonic matter. Now, to look forward in time and to figure out what kind of a universe we live in, we can't go forward in time, but we can go backwards in time, measure what the universe was doing at progressively different times in the past, and then figure out which one of these curves the universe actually fits on. So, and that again gets back to the idea of the cosmic look-back time. Astronomy is a time machine. We never see anything in the universe as it is, we see it as it was. It takes light 8 minutes to reach Earth from the sun. So every time we look at the sun, we're seeing the sun as it was 8 minutes ago. Now, here on Earth, light travels pretty fast. So we see essentially things instantaneously. But the farther out into space we look, the further back in time we're looking. So we see Sirius as it was 8 years ago. We see other stars around us as they were some hundreds or even thousands of years ago. We can look back and see the galaxies as they were millions or even billions of years ago. So we can measure, through the look-back time, we can measure the expansion rate of the universe as it was at progressively different times into the past. And in the 1990s, there were two teams that did this. The so-called High-Z supernova search team, led by Brian Schmidt, and the competing supernova cosmology project, led by Saul Perlmutter. And these two teams, it was a fierce competition. They didn't like each other, as you can see by this photo right here. Competition is good, though. It keeps everybody on their toes and basically makes sure that everything is done in the right way, and that whatever results were obtained, that you would check the results to make sure that you were getting the right information. Basically, to measure the expansion rate of the universe, you do it two ways. Number one, you measure the redshift. All you got to do, pretty simple. Galaxy spectrum determines the redshift of the galaxy. And then you measure what's called the distance, the luminosity distance. Now, distance is one of the biggest problems in astronomy to tackle. Nearby stars, fairly easy using trigonometric parallax techniques. But measuring the distance to galaxies far and far away is a difficult problem to solve. But essentially, to simplify it, you can do something what's called a luminosity distance. If I know how bright something appears, I can measure the intrinsic brightness. I can measure the, not the intrinsic brightness, but the brightness of a star as it appears here on Earth. Then I can measure its distance if I know how intrinsically bright it is. And that's basically just the inverse square law here. So you measure the luminosity of an object using standard candles. A standard candle is an object, okay, here you can see redshift. So you can see the redshift of some of the objects, classes of objects in the universe. So you can see, for instance, a Type 1a supernova from 1994. At the time, the most distant Type 1a supernova is about 5 billion light years away, had a redshift of 0.425. The most distant Type 1a supernova ever had a redshift of 1.9. Basically, redshift, Z, the greater the number of Z, the higher the value of Z, the greater the redshift. So you can go all the way from 0.4 up to the cosmic microwave background, which is the relic radiation left over from the Big Bang, has a redshift of a little over 1,000. The most distant galaxy, gamma ray burst, quasar, Type 1a supernova, etc. So, again, you can measure the redshift of a galaxy, and then you can calculate its distance using the luminosity distance relationship. If I know how intrinsically bright something, if I know how bright something appears in the sky, and I know its intrinsic brightness, then I can measure how far away it is. We do this every day. Good example is like a 100-watt light bulb. If a 100-watt light bulb is close to me, it's going to appear brighter than it's on the other side of the room. My eyes can calibrate the intrinsic the distance of that to that 100-watt light bulb based on how bright it appears. Now, intrinsically, it's 100 watts. 100 watts is 100 watts. But if it's closer to me, it's going to appear brighter than if it's further away. Same kind of thing in astronomy. So if I know how intrinsically bright something is, I can figure out how far away it is just basically using the inverse square law. Now, the problem is I need to have a bright enough standard candle to be able to see it at vast distances. And here you can see kind of a breakdown of the cosmic distance ladder. Cepheid variables are great, but they don't get you very far in the universe. They only get you out to about the Virgo cluster. We need a really, really bright standard candle to see all the way across the universe. And fortunately, we have one in the Type 1a supernova. Now, supernova is an exploding star. Our sun won't explode into a supernova, but more massive stars will. And a Type 1a supernova occurs when a dense nugget called a white dwarf in a binary star system gravitationally accretes mass from a nearby companion, as you can see here. So if you have a dead white dwarf star and then its companion star moves off of main sequence, swells up into a red giant star, the outer layers could get sucked onto the star, the white dwarf, gravitationally, leading to a thermonuclear runaway. Now, Chandrasekhar calculated what this limit was. It's about 1.4 solar masses. So if it approaches 1.4 solar masses and exceeds it, then it'll explode. The reason why, and here you can see white dwarf, our sun will become a white dwarf in about 7 billion years. It'll run out of hydrogen, it'll go through the helium burning, the helium flash, and basically what will be left over at the end of its lifetime is a carbon-oxygen core, white dwarf. during a type 1a supernova explosion, the carbon and oxygen are converted into nickel, which is very, very bright. So a type 1a supernova is like a 1.4 solar mass thermonuclear bomb going off. And it's about 5 billion times brighter than our sun. To put this in perspective, when a type 1a supernova occurs, it can outshine an entire galaxy of stars briefly. And you can see some examples here. Supernova 1994D. Here's its host galaxy in the Virgo cluster. Here's the type 1a supernova. 2011, the closest type 1a supernova ever observed was in the Pinwheel galaxy, about 20 million light years away. Great opportunity to study up close what a type 1a supernova is like. The reason why a type 1a supernova is such a good standard candle is because they all occur at about the same mass, 1.4 solar masses. So the physics of it is about the same. So we need the same brightness, the same brightness across the board as we're doing a type 1a in order for a standard candle to work. So here you can see the light curve. Basically, you have a moment of peak brightness and then it falls off systematically. And that's one of the ways we can tell that it's a type 1a supernova. Now, not all type 1a's are exactly the same. In order to make them a true standard candle, they had to be calibrated in order to become a standard candle. And Mark Phillips and Mario Hume were the ones who did the work to actually calibrate type 1a supernovas to become standardizable as a standard candle. And the way this was done is he discovered that there was a relationship between the peak luminosity of a type 1a and then its decay rate, or basically its speed of luminosity evolution after maximum light. So the brighter a type 1a, the longer it takes for it to fall off. So there was a systematic relationship between how bright it is and how long it takes to actually fall off. And here you can see the data. So up here, this data is kind of a mess, really hard to use it as a standard candle. But applying the Phillips correction, you get a tight curve that we can now use to use all type 1a supernovas as they occur across the universe as a type of standard candle. They're great. The problem with type 1a supernovas is they don't occur very often. In a typical galaxy like our Milky Way, you may only have a supernova event occur once or twice every millennium. The last one occurred in the early 1600s. We're overdue. They're also random. There's no advance warning of where to look, and they're fleeting. Once they happen, you got to be on your game and ready to observe them. So if there's a galaxy that you're very fond of, you could either sit there, look through the telescope 24 hours, 365, 7 days a week until you actually observe a type 1a supernova, in which case you're going to be doing that for quite a while. Or you can do the next best thing. Fortunately, there's a lot of galaxies in the universe, and somewhere in the universe, a supernova occurs approximately once every second. So we got to look at thousands of galaxies all at once in order to observe a handful of type 1a supernovas. So we're looking at anywhere from 5,000 or more galaxies at a time in order to get a handful of type 1a supernovas. So essentially, we're putting the universe on surveillance. And technology has enabled us to do this. I mean, we have the Keck telescope now in Hawaii, obviously the Hubble Space Telescope, Cerro Tololo in Chile. This is astronomy's version of conspicuous consumption. Big glass, both on Earth and in the sky. So, yeah, we like to spend money in astronomy too. So this is how we make big discoveries in astronomy. And of course, not only the size of the telescopes, but the invention of the CCD chip, the Silicon Revolution, really propelled astronomy forward too. Here's the Pan-STARRS telescope in Maui, Hawaii, and it contains the world's largest digital camera, 1.4 gigapixels. When the initial discovery was made, it was the early 1990s, mid-1990s, so we had Pentium 1s, and we had, 4 megapixel cameras. Today, we've come quite a bit further. So basically what you do is you take snapshots of thousands of galaxies looking for a supernova, and you just look for arrows. And anywhere you see an arrow, you see a supernova. So obviously it's a little bit more involved than that. Otherwise, you know, they wouldn't give out Nobel Prizes for this kind of work. But here you can kind of get an idea of how this works. Keck in Hawaii, Berkeley, Cerro Tololo in Chile, the Hubble Space Telescope. You're basically taking a snapshot of thousands of galaxies in one field, anywhere from 50 to 100 fields in one image. And then you look for, you're observing tens of thousands of galaxies in 3-week intervals between new moons. So you get out there, you observe during one new moon, you go back 3 weeks later, take the same snapshot of the sky 3 weeks later, and then you look for a difference between each of the fields. So in one field you may not see anything, and then a week later you may see an event that looks like a supernova. Here's an example of that from the Supernova Cosmology project. Observing a field of galaxies, one little image here, you can see what the galaxy looked like 3 weeks before, and then you look at it 3 weeks after, and you can see a difference in luminosity, indicating that there's something going on there. Now, it may be a cosmic ray, it could be a comet, but it could also be a supernova event. Just don't know until you analyze the data. So, both teams did this systematically, and they plotted the data, and this is basically the results of what they discovered. Now, again, Hubble diagram, the greater the z, this is the redshift on the horizontal axis. The greater the value of z, the greater the redshift. The further out into space you're looking, the further back in time you're looking. And what they discovered was completely counterintuitive. The data were falling above the line. Now, this is the inverse of the Hubble diagram that Bill showed you. So in Bill's diagram, if it's curving up, if it's actually curving down, that would indicate an accelerating universe. This is the inverse of that. So the data is curving up, indicating that the universe is accelerating. Now, what does that mean? If I look further out into space and I look further back in time, intuitively I would expect to see the expansion rate faster the further out into space that I look. Big Bang model. Again, if the universe had an origin, then it should have expanded more quickly in the early stages of the universe and then slowed down with time if all the galaxies were pulling on each other. So I expect to see a universe that is expanding faster in the distant past and more slower in the recent past. But that's not what these guys discovered. They discovered a universe that was actually expanding slower in the past and faster in the more recent past. Completely counterintuitive. The the two teams analyzed distant and nearby supernova, and they discovered that these supernovae right here are very, very faint. They're far fainter, basically, than they have any reasonable right to be. And that's a clue to an accelerating universe. So looking at a different plot here, going further out, the highest redshifted supernova were fainter than would be expected even if you had an empty universe. Okay, what does that mean? Getting back to the apple analogy. If I throw the apple up, the gravity of the Earth pulls it back down. Now imagine the Earth doesn't even exist and I throw the apple up. What happens? It just keeps going. All right? If the apple is analogous to the supernova, the most distant supernova were further away than if I'd thrown the apple up and the Earth didn't even exist, where that apple would be. In other words, I'd have to attach a rocket to this apple to get it into a position of where it would be if it was analogous to some of these distant supernovae. So you're seeing they're falling on a plot here that curves upwards. This is actually the opposite of the plot that Bill showed in his presentation. The upward curve in his was a decelerating universe, downward was acceleration. This data is just flipped. So if it goes up, then it's accelerating. Yeah.
Moving further
Yeah, that's a great question. I'm going to answer that question in just a minute. That's an awesome question. Basically what she's asking is, if I can paraphrase, how do you know that they're not fainter because of dust? So maybe dust is dimming the supernova. If you want to appear to ask an intelligent question on an astronomy lecture, it doesn't matter what the lecture is on. Just ask one question. How would dust affect your results? Because we lived in a dusty universe. So that's an excellent question. It tells me you're listening. I'm going to come back to that question though. So anyway, getting back to the data, it's falling on a curve that's telling us that the universe is accelerating. Expecting this, instead we're getting this. So getting back to our plot. Again, assuming matter is the only thing that makes up the universe, the data is not following this trend, and it's not following any of these trends. It's actually following this trend right here, which tells us that there's got to be something else other than matter making up the universe. So here's a snapshot from Adam Riess, one of the Nobel Prize winners, lab notebook. And you can see here that for an omega lambda term of 0, according to the supernova data and the measurements, he was getting a matter density of negative 0.36. Of course, he forgot to put the 0 in there. But anyway, that's kind of strange because I exist and you exist. So how can we have a universe with negative matter? So it's kind of like one of those moments in science where you're like, oh God, what did I do wrong? It wasn't, I made a discovery. It was like, I made the wrong measurement. I made a mistake. I've got to go back and check and see what's going on. But it gave us a clue that, it gave these guys a clue that a discovery had been made. So emails at the time back and forth between the different members of the Heisey redshift team kind of imply that they're struggling, wrestling with the results, because they went back, did the measurements again, came up with the same result. So here's Alex Filippenko, the great astrophysicist from Berkeley. Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. Brian Schmidt, Australia, another Nobel winner. Again, right around the same time. It is true that the supernovas say that the cosmological constant is greater than 0. How confident are we in these results? I find it very perplexing. Again, this is strange. Mark Phillips, as serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. Finally, Adam Riess, sent on the eve of our honeymoon over understandably icy stairs from my wife. Hey, the honeymoon can wait, all right? I'm working on a Nobel Prize. The results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I have. And I wanted to get further into writing the results up before the other team got wind of it. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers after all. That's the key. We're observers. You go into an experiment expecting one result, a universe that is either going to slow down or is going to recollapse. Instead, you see a result that's just, it's like that multiple choice answer in college, or you take on a test, right? None of the above. It's not A, B, C, or D. It's E. It's none of the above. Accelerating universe was not on the docket. Nobody would have predicted a cosmological constant 20 years ago. So the upshot of it is, remember that lambda term that Einstein introduced into his equations of relativity and then threw out? Well, 70 years later, we've reincarnated the idea, and it seems to be the dominant stuff that the universe is made out of. So here you see him sad and despondent. Did he ever introduce the cosmological constant in the first place? So if he was alive today, I don't know, maybe his reaction would be that. And that, of course, led to the discovery of the accelerating universe and the Nobel Prize. And here you can see Einstein, very, very surprised, not because he's blowing parallel universes from his pipe. And for those of you who don't know, parallel universes come from the pipes of theoretical physicists. But he's even more surprised because these guys got the Nobel Prize and not him for something that he invented, but he didn't have the courage to follow through with his convictions. He introduced it and then threw it out. But he missed a golden opportunity to predict by theory or first principles an accelerating universe. Okay, so was the universe always accelerating? Maybe at one time in the distant past, the universe was smaller, the matter density was higher, so maybe the universe was decelerating in the past and then accelerating. So to answer that question, Adam Riess, a few years later, formed the higher Z team and went out and measured even more distant supernova. And sure enough, he found that it follows this curve right here. So the upshot of it is, about 5 billion years ago, the universe went through a transition from expanding but slowing down in its rate of expansion to speeding up. In other words, it went from a transition from deceleration to acceleration. Well, the technical term in physics for a transition from deceleration to acceleration is called a jerk. So you have position, velocity, acceleration, and jerk.
But it was always expanding?
It was always expanding. It was expanding but slowing down in its rate of expansion because the universe was smaller and denser at that time, so the gravity from matter and dark energy was stronger because the matter density was higher. So there was this tug of war going on between dark energy and dark matter. And early in the universe, dark matter was basically winning, slowing down the rate of expansion. Then the universe expanded far enough so that it diluted the energy density or the matter density sufficiently so that dark energy could take over. And that's where you had that transition from deceleration to acceleration. So again, the change from deceleration to acceleration is called a jerk. So right after this result came out, the New York Times posted this newspaper article. Now, if you're like me, you rarely actually ever read the article. You just read the headline and then you look at the picture. So you can imagine that Adam was not too pleased when his colleagues were getting questions like, you know, who's this cosmic jerk that you work with that reversed the universe? So anyway. Okay, now, kind of getting back to your question. So maybe you're skeptical of the supernova data. Maybe dust dims the supernova, even though there are ways around that. That's basically what Adam Riess's master's thesis was about, doing light curve shaping to rule out the effects of dust. But maybe, maybe it's dust that's dimming the supernova, or maybe the physics of type 1a supernova was different in the distant past. We have an accelerating universe. Extraordinary claims require extraordinary evidence. So you're looking at a baby picture of the universe. This is the cosmic microwave background taken by the WMAP, the Wilkinson Microwave Anisotropy Probe. You're looking at an image of the universe when it was about 375 or 379,000 years old. And each one of these little spots represents a slight variation in the temperature of the early universe. So these are hot spots and these are cold spots. 1 part in 10,000, so it's very, very small. And this, of course, was discovered by Arno Penzias and Robert Wilson in 1964. They eventually won a Nobel Prize for it. It's the smoking gun for the Big Bang model of the universe. It's the most perfect black body that we've ever seen. We can't even simulate a black body like this in the lab. Now, we can use the WMAP data to measure the geometry of the universe. So a quick review here of the geometry of the universe. If omega being the total density of stuff, everything that makes up the universe, if that parameter is equal to 1, we have a flat universe, like a Euclidean sheet of paper. If omega is greater than 1, we have a higher density universe, which is basically a closed universe. It's like a sphere. So it's a universe that will expand and then contract back on itself. If we have an underdense universe, that would be like a saddle shape, open universe. So you can measure the geometry of the universe by looking at these little fluctuations in the cosmic microwave background, and also by measuring the angles of a triangle. So the interior angles, if they add up to more than 180 degrees, you've got a closed universe. Less than 180 degrees, you've got an open universe that's saddle shaped. If it's exactly 180 degrees, you've got a flat universe. The WMAP data points to a flat universe. And again, you just measure the very tiny fluctuations in the background. What this tells us is that matter is not enough to account for the geometry of the universe. Matter only gives us about 30% of the critical density. When I say matter, I'm talking about baryons, which is basically atoms, the stuff that you and I are made up of, and then also dark matter. There's about 10 times more dark matter in the universe than there is ordinary matter. So you add up all the matter, And the matter density of the universe only gets us about 30% of the critical density. So you need a significant non-matter component or energy component to get a spatially flat universe based on the geometry measured from the W map. Okay, Baryon acoustic oscillations. It turns out that there is a one-to-one correspondence between the slight density fluctuations in the cosmic microwave background and the positions of galaxies in the universe today. Back when the universe was hot and dense and opaque before the moment of last scattering, the slight differences in density translated into gravitational potential wells that were sucking in the baryons, and then the photons were pushing them back out. And that created an effect, kind of like sound waves rippling through the early universe, analogous to throwing a stone in a pond and then those ripples go out. Well, when the universe expanded and cooled, that pattern was frozen into the universe, and we can measure it today. This is a technique independent of the supernova data. That's the point. Instead of a standard candle technique for measuring the universe, we now have a standard ruler, about 490 million light years. So this is another clue to the existence of dark energy when you have independent techniques. And the Baryon acoustic oscillations, again, positions of galaxies in the universe. You can measure statistically where they're likely to occur based on the density and the distribution of matter. But also the equation of state points to the nature of the dark energy being more like a cosmological constant. So adding this all up, we've got 3 independent techniques: supernova data, accelerated expansion, cosmic microwave background that tells us something about the geometry of the universe, spatially flat, and then also the Baryon acoustic oscillations. You map it all out, and where they converge gives us this picture of the universe. 30% matter, 70% energy, or cosmological constant like. And that leads to the so-called Lambda CDM model of the universe, which is the standard cosmology model. Lambda being your cosmological constant, CDM being cold dark matter. Age of the universe, 13.79 billion years. And I need to update this because I put this together 2 weeks ago, so I need to add another 2 weeks to the age of the universe. Another joke. From the Planck mission, the Hubble constant, the density of baryons or ordinary matter, about 4.8%. So that's all the baryonic matter, all the atoms in the universe. Cold dark matter, 25.8%. Cosmological constant, about 69%. So the universe is made up, 69% of the density of the universe is anti-gravity or energy. Okay. So we talked about the evidence for the existence of dark energy, but what is it? The short answer is we don't know. But we can at least talk about some of the default hypotheses for what the dark energy could be. Now, quick review of gravity. Newton versus Einstein. In Newtonian gravity, basically it's just the mass of one object and the mass of another object and the distance between them. So the apple falls to the earth because of the mass of the earth and the mass of the apple and the distance in between them. But in general relativity, there's this pressure term. What do we mean by pressure? The earth exerts an outward pressure on me that keeps me from falling to the center of the earth. And that outward pressure translates into an inward gravitational pull. So I weigh a little bit more on the surface of the earth when I do it with general relativity as opposed to Newtonian gravity. Now it's virtually negligible, but if I was standing on a really, really dense object like a white dwarf or a neutron star, then there would be a significant difference. Well, the rate of expansion of the universe is proportional to this term right here, the energy density and then the pressure. So, but if the universe was filled with a negative pressure, you could make this, so it's negative, meaning it's a decelerating universe. By default, mathematically, it's set up as a decelerating universe. But if you had a substance of negative pressure, you could make the whole term positive and have an accelerating universe. So if space were filled with a substance of negative pressure, great enough to overcome the positive energy density, the net effect would be repulsion, and we think that the dark energy is something like that. So one idea we've got to get into the quirky world of quantum mechanics, are the quantum fluctuations in the vacuum, otherwise known as the zero-point energy of the vacuum. Now, we were all taught from the time that we were very, very young that the vacuum is completely empty, sheer nothingness. Turns out that's not exactly true. According to the Heisenberg uncertainty principle, there have to be little particle and antiparticle pairs coming into and flashing out of existence all the time. So neutrinos and antineutrinos, quarks and antiquarks, protons and positrons or antiprotons. Basically, they flash into existence, exist for a brief moment, and then they annihilate each other. It was always believed that the net effect would be zero. But if there was a positive energy that resulted from this, then you could have space filled with a vacuum energy that could cause the universe to stretch. What's the empirical evidence or the experimental evidence for this? The measured levels of the hydrogen atom, the measured energy levels of the hydrogen atom do not agree with the theoretical predicted energy levels of the hydrogen atom when you do not take into account the quantum effects. It's called the Lamb shift. So you need quantum mechanics to accurately measure or get the measured results of the hydrogen atom to agree with theory. Theory and measurement don't agree if you don't take the quantum effects into account when you're measuring the energy levels of the hydrogen atom. Another experiment is the Casimir effect. You can put two parallel plates in a vacuum, two massless plates, let them sit there, and they slowly go together. Why? Because the vacuum pressure outside of the plates pushes on them, and the pressure outside the plates is greater than the pressure between the plates because of the boundary conditions between the plates. So the vacuum has energy. So the upshot of it is maybe the dark energy is just the quantum energy of the vacuum, and we're done. Well, there's just one little problem. When we do a quick back-of-the-envelope calculation for how much dark energy there should be in the universe versus how much we actually see, we come up with just a little discrepancy. We're only off by 10 to the 120th power, 20 orders of magnitude higher than a Google. So you're in graduate school, you're taking one of Bill Bustler's classes, he gives you a test, and you get the wrong answer. And then you go to his office the next day and you want to argue the result. I mean, that's how I got through graduate school, right? It's not what you know, it's how well you negotiate with professors. So, you know, Bill, I don't understand why you gave me the wrong answer on this test question. I was only off by 10 to the 120th power. I mean, come on, man, show me some love. Probably not going to win that argument, especially coming from a guy who's known for telling you that the answer is sometimes 3 or 4 significant digits out. So, this has been called the worst theoretical prediction in all of science. Vacuum catastrophe, essentially. Now, I would tend to argue that it's just an incomplete. We're not far enough along yet to really understanding the nature of what's going on. But the quantum energy of the vacuum as an explanation for dark energy is out. So one of the huge mysteries with dark energy is why is it so small? I mean, it causes the universe to expand on large scales, but it's virtually indetectable on the everyday scale. There's no way we can measure it. So it's not like we could harness this stuff and add it to our cars and levitate over traffic and fly. We can't harness the zero-point energy of the vacuum. So another idea is quintessence. You know, when in doubt, add a scalar field. So the cosmological constant is constant and uniformly distributed. Quintessence is dynamic. It could change over time. Quintessence comes from the Aristotelian fifth essence that supposedly makes up the rest of the universe. So you have water, fire, earth, and air, and then you have the quintessence, or the fifth essence. That's where the idea comes from. The best way to understand the quintessence is through the concept of symmetry breaking. So water droplets are more symmetrical than ice crystals. So when you go from water to ice, you're breaking symmetry and releasing some heat into the surroundings. And you could actually do this. You could have a liquid that has a certain latent heat associated with it. So it's still in the liquid form, even though it's below its freezing temperature. And then you can manipulate it so that it freezes and then releases heat into the surroundings. So that same concept, again, when you're going from vapor to liquid to water, energy is released into the medium. So that's the idea. So maybe the universe has a force field associated with it that's analogous to some kind of latent heat stored up. And when that latent heat is released, it causes the universe to expand. Not likely. The evidence seems to point to more of a cosmological constant idea for dark energy. Or the third idea is maybe Einstein is wrong. This really keeps the theorists up late at night. Maybe we need a new theory of gravity, one that says that gravity is repulsive on large scales instead of attractive. Again, it's really hard because general relativity works so well. It even has engineering applications. How many of you in here have used GPS in the last day or two? GPS does not work if you don't take into account general relativity, because the Earth orbiting satellites are further away from the Earth's gravity, and clocks tick faster on board the Earth orbiting satellites than they do on the ground. So you got to take into effect the time dilation effects due to gravity. It translates to about 6 miles a day, and you don't want to get lost in Memphis this time of night. So you want to make sure your GPS is working. You can end up in a bad place. So general relativity works. Bottom line is, to understand dark energy, we need to bridge the gap between general relativity and quantum mechanics, and these two theories hate each other. We need some theory to unify these two. And quite frankly, we're not even close. So we got a lot of work to do. Okay, so here we go. Big Bang, which is a terrible term, by the way. Think about it. Big Bang. That is the worst term in all of science. It wasn't big, and there was no bang. The universe was a singularity, and there was no medium for anything to travel through. And it also gives you this picture that the universe sort of like an explosion, all these bits of stuff flying out from a singularity. That's not what happened. The universe supposedly went through a period of rapid inflation where it went from boom to boom in the blink of an eye. Between 10 to the minus 36 and 10 to the minus 34 seconds, supposedly the universe grew by a factor of 10 to the 40th, the rapid inflation. We see that because how can you have points, different points in the microwave background that are connected over large distances. But anyway, so you have a Big Bang, you have a period of expansion, but decelerating expansion, your cosmic jerk, and then you have accelerating expansion. And now looking off into the distant future, one of three fates. Either a universe that will recollapse into a big crunch or rip itself apart. And that depends on the nature of dark energy. So if dark energy is more quintessence-like, in other words, dynamic, and can change with time, then you can have a big crunch scenario where it changes signs and then the universe collapses back in on itself. Again, not likely, but it hasn't been completely ruled out yet. The opposite of that is a big rip effect, where the universe expands and then the dark energy strength increases with time, and you not only have accelerating expansion, but you have accelerating expansion. So the dark energy is really, really small now, but trillions of years into the future, the dark energy is so strong that it rips everything apart. Basically galaxy structures, then galaxies themselves get ripped apart, then individual stars, planets get ripped apart, and then eventually individual atoms. It's kind of a fun way to think about the universe ending, you know, just everything just gets ripped to shreds. But in the 20 years since the discovery, that's kind of ruled out. If the equation of state is significantly negative, this could happen, but again, it's not likely. The most likely scenario is a cosmological constant that's constant, uniformly distributed, and you get a universe that just expands and cools forever. So, 100 billion years into the future, the universe keeps going like it is. Basically, you only see the Virgo cluster of galaxies. There's no cosmic microwave background. It's too far away. There's no evidence for an expansion. And then you would conclude that the universe is small and static, if there's any living creatures. 100 trillion years into the future, it's the death of stars. So most of the baryonic matter in the universe right now is locked up in interstellar and intergalactic gas. That's basically the raw material for forming stars. Well, there's only a finite amount of matter. And as gas compresses due to gravity and forms stars, and you go through the life cycle of stars, every time around, more and more matter is locked up into stellar remnants. Our sun will become a white dwarf. More dense stars, more massive stars will become neutron stars and black holes. So every time you go through the stellar cycle, gravity takes its cut, and more of the matter is being used up. You know, supernova spews the stuff back out in the interstellar medium, but hydrogen is converted into metals. And then stellar remnants, more and more of the mass is tied up in stellar remnants. So if you go forward trillions of years into the future, all you have are basically stellar corpses. So you can envision a scenario, if there's any life, which there won't be, huddled around a dim, dying red dwarf star. The white dwarfs will become black dwarfs, the red dwarfs will become black dwarfs. So that's trillions of years into the future. 10 to the 17 years, solar systems evaporate. Stellar encounters are very rare, but given enough time, eventually stars will interact and gravitationally they will rip planetary systems apart. 10 to the 27 years, galaxies start to dissolve. So all you have are stellar remnants. They gravitationally interact and they either fling out of a galaxy or they get thrown into the supermassive black hole. 10 to the 32 years, matter dissolves. There are some quantum mechanical models that suggest that even protons themselves are not stable and they'll decay into electrons, neutrinos, and positrons. So matter itself has only a finite life. 10 to the 67 years, stellar mass black holes evaporate due to Hawking radiation. And then 10 to the 100 years, the supermassive black holes at the center of galaxies eventually will dissolve in a flash of gamma rays. So the end result is a big chill, supposedly, according to current models. So summing it all up, I think this poem by Robert Frost probably says it best. Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So, the bottom line is, if you want to see the universe, you got to come out to tomorrow night's observing session. It's not going to be around forever. All right, thanks.
Thank you very much, Jeremy.